हेलो व्यूअर्स। तो टुडे हम लोग आज पढ़ने जा रहे हैं चैप्टर फर्स्ट फिजिक्स का क्लास 9th का। तो इसका जी अगर बेसिकली साइंस की बात की जाए तो साइंस का ये चैप्टर नंबर 7 और फिजिक्स का चैप्टर नंबर 1 है। तो हम लोग आज इसको समझने जा रहे हैं, रीडिंग करने जा रहे हैं हम लोग इसकी। तो in everyday life we see some object at rest and other in motion. Bird fly, fish swim, blood flow through the veins and arteries, and the car moves. Atoms, molecules, planets, stars, and galaxies are also in motion. We often perceive an object to be in motion when its position changes with time. However, there are situations where the motion is inferred through indirect evidence. For example, we infer the motion of air by observing the movement of dust and movement of leaves and branches of trees. Uh, what causes the phenomena of sunrise, sunset, and changing of season? It is due to motion of the earth. If it is true, why don't we directly perceive the motion of the earth? An object may appear to be moving for the one person and stationary for some other. For the passenger in a moving bus, the roadside tree appeared to be moving backward. A person standing in a roadside perceived the bus along with the passenger as the moving. However, a passenger inside the bus see his fellow passenger to be at rest. What do these observation indicate? Most motion are complex. Some object may some object move in a straight line. Other take a circular path. Some may rotate, and a few other may vibrate. There may be situation involving a combination of these. In this chapter, we shall first learn to describe the motion of an object along a straight line. We shall learn to express such motions through a simple questions and graph. Later, we shall discuss way of describing circular motion. 7.1 Describing motion. We describe the location of an object by specifying a reference point. Let us understand this by an example. Let us assume that a school in a village is 2 kilometers north of the railway station. We have specified the position of the school with respect to the railway station. In this example, the railway station is the reference point. We could have also chosen other reference point according to our convenience. Therefore, to describe the position of an object, we need to specify a reference point called the origin. 7.1.1 Motion along a straight line. The simplest type of motion is the motion along a straight line. We shall first learn to describe this by an example. Consider the motion of an object moving along a straight line path. The object starts its journey from O, which is treated as its reference point. 7.1 Let us A, B, C and represent the position of object at different instants. At first, the object comes through B and C and reaches A. Then it moves back along the same path and reaches C and B. The total path covered by an object OA plus AC, that is 60 km plus 30 km is equal to 19 km. This is the distance covered by an object. To the described distance, we need to specify only the numerical value and are not direction of the motion. There are certain quantities which are described by the specifying only their numerical value. The numerical value of a physical quantity is its magnitude. From this example, can you find out the distance of the final position C of the object from the initial numerical value of the displacement of the displacement of the object from O to C through the shortest of distance measured from the initial to the final position of an object is known as the displacement. Can a magnitude of the displacement is equal to the distance? Example is given in figure 7.1 for motion of our object from 0 to O to A. The distance covered in is 60 km and the magnitude of the displacement is also 60 km during the motion from O to A and back to B. The distance covered is equal to 60 kilometer plus 25 kilometer is equal to uh, 85 kilometer, while the magnitude of the displacement is equal to 35 kilometer. Thus the magnitude of displacement 30 kilometer is not equal to the path length is equal to length 85 kilometer. Further, we will notice that the magnitude of the displacement of a course of motion may be zero, but the corresponding distance covered is not zero. If we consider the object is to travel back to O, the final position coincides with the initial position, and therefore the displacement is zero. However, the distance covered in a journey O is OA plus AO is equal to 60 kilometer plus 60 kilometer is equal to 120 kilometer. Thus, two different physical quantities, the distance and displacement, are used to describe overall motion of an object and to locate its final position with the reference to its initial position a given time at a given time. uh, 7.1.2 uniform motion and non-uniform motion. Consider an object moving along a straight line. Let it travel 5 meter in the second first second, 5 meter more in the next second, 5 meter in the third second, is 5 meter in 5 meter in the fourth second. In the case the object 5 meter in second, as the object cover equal distance is equal interval of time, it is said to be in uniform motion. The time interval in the motion should be small. In our day-to-day life, we come across motion where object cover unequal distance in equal interval of time. For example, when a car is moving on a crowded street, or a person is jogging in a park, there are some instances of non-uniform motions. Here you see the some table 7.1 is given, and the measuring the rate of motion. Look at the situation given in figure 7.2. If the bowling speed is for 143 kilometer per h minus 1 power minus 1 in figure 7.2a, what does it mean? What do you understand from the signboard in 7.2b? Different object may take different amount of time to cover a given distance. Some of them move fast and some move slowly. The rate at which object move can be different. Also, different object can move at the same rate. One of the way of the measuring the rate of the motion of an object is find out the distance traveled by an object in unit time. The quantity is referred to be as speed. The SI unit of the speed is meter per second. This is represented by the symbol meter second minus power minus 1, or m dash as intercost. As the other unit of the speed include the centimeter per second, centimeter s power minus 1, and kilometer per hour, kilometer power h kilometer per hour minus power minus 1. To specify the speed of an object, we require only its magnitude. The speed of an object need to be constant. In most cases, object will be in non-uniform motion. Therefore, we describe the rate of the motion of such object in terms of their average speed. The average speed of an object is obtained by dividing the total distance by the total time taken. That is average speed. sorry, average school, there we see the formula of average speed is equal to total distance traveled upon total time taken. If an object travel a distance as the time taken, the time, then its speed v is equal to s upon t. Let us understand this by an example. A car travel a distance of 100 kilometer in 2 hours. Its average speed is 50 kilometer per hour. इसकी power -1, the car might not have traveled at 50 kilometer per hour all the time. Sometimes it might have traveled faster, sometimes slower than this. Example 7.1. Here we so leave it the example. This is a numerical part of the question, and we are just going put forward reading on 7.2.1. Speed with direction. The rate of the motion of an object can be more comprehensive if we simplify specify its direction of the motion along with its speed. The quantity that specify both these aspects is called velocity. The velocity is the speed of an object moving in a definite direction. The velocity of an object can be uniform or variable. It can be changed by changing the object speed, direction of the motion, or both. When an object is moving along a straight line at a variable speed, we can express the magnitude of its rate of the motion in terms the average velocity. It is calculated in the same way as we calculated average speed. In the case the velocity of object is changing at the uniform rate, then the average velocity is given by the arithmetic mean of the initial velocity and the final for a given period of time. That is, average velocity is equal to initial velocity plus final velocity upon 2. Mathematically, we can write the given equation where VAV is the average velocity, U is the initial velocity, and V is the final velocity of object. Speed and velocity have the same unit time, is that is ms or meter dash s. Here see the activities and questions that given, and here see the question of velocity, how to find velocity in this question, and here we the other example. And now we just going on the rate of change of velocity. During uniform motion of an object along the straight line, the velocity remains constant with time. In the change in velocity of the object for any time interval is zero. However, in non-uniform motion, velocity varies with the time. It has different values at different different point of the path. Thus, the change in velocity of object during any time interval is not zero. Can we now express the change of velocity of an object? To answer such a question, we have to introduce another physical quantity called the acceleration, which is the measure of the change in velocity of an object per unit time. That is, acceleration is equal to change in velocity upon time taken. If the velocity of an object changes from the initial value u or to the final value v in time t, acceleration is a we here see the formula of it, and this kind of the motion is known as acceleration motion. The acceleration is taken to be positive if it is in direction of velocity, and negative when it is opposite to the direction of velocity. The SI unit of the acceleration is meter second की power -2. If an object travel in a straight line and the velocity increases or decreases by equal amount in equal interval of time, then the acceleration of object is said to be uniform. Motion of a freely falling body is an example of uniform acceleration motion. On the other hand, an object can be travel with a non-uniform acceleration if its velocity changes at a non-uniform rate. For example, if a car travel along a straight road, increasing its speed by unequal amount in a equal interval of time, then the car is said to be moving with a non-uniform acceleration, attaining a velocity 6 meter per second in 30 seconds, and then he applies brakes such as the velocity of the bicycle come down 4 second in next 5 seconds calculate the acceleration of the both. Here we see the example, question numerical subheading, and here we see the questions. Now, graphical representation of motion. Graphs provide a convenient method to present basic information about varies of the of event. For example, in the telecast of the one-day cricket match, vertical bar graph show a run rate of the team in each row. As you studied in mathematical, a straight line graph help in solving a linear equation having two variables. To describe the motion of an object, we can use the line graph. In the case line graph, so dependence of one physical quantity such as the distance or velocity on another quantity such as a time. Distance time graph, the time in the change in the position of an object with time can be represented on the distance time graph adopting to a convenient scale of choice. In the graph, time is taken along the x-axis and the distance is taken along the y-axis. The distance time graph can be employed under various conditions where object move with a uniform speed and non-uniform speed remain at a rest. We know that here we see the graph, distance time graph of object moving with a uniform speed. Here we see the graph, and now we keep moving on our further reading. We know that the when an object travel equal distance in equal interval of time, it moves with uniform speed. This shows that the distance traveled by an object is directly proportional to time taken. Thus, for uniform speed, a graph of distance travel against time is a straight line as so in figure 7.3. The portion OB of the graph so that the distance is increasing at a uniform rate. Note that you can also use the term uniform velocity in a place of uniform speed if you take the magnitude of the displacement equal to the distance traveled by the object along with the y-axis. We can use the distance time graph to determine the speed of an object. To do so, the graph in figure 7.3 draw a line parallel to the x-axis from the point A and another line parallel to the y-axis from point B. These two lines meet each other at a point C to form a triangle ABC. Now on a graph, AC denotes the interval T2 minus T1 while BC correspond to the distance S2 minus S1. We can see from the graph that object moves from the point A to B. It cover a distance S2 minus S1 in time T2 minus T1. The speed V of the object. Therefore, we can represent as here we see how we can represent V is equal to S2 minus S1 upon T2 minus T1. We can also plot the distance time graph of for accelerated motion table 7.2. So the distance traveled by a car in a time interval of the 2 seconds. Here we see the graph table 7.2, and here we see the time graph. The distance time graph for the motion of the car is so in figure 7.4. Note that the shape of the graph is different from the earlier distance time graph figure 7.3. The uniform motion nature of the graph so the non-linear variation of the distance traveled by a car with the time. Thus the time graph shown in 7.4 represent the motion with a non-uniform speed. Velocity time graph, the variation in velocity with time of an object moving in a straight line can be represented by velocity time graph. In the graph, time is represented along the x-axis and the velocity is representing along the y-axis. If the object moves at a uniform velocity, the height of an object velocity time graph will not change with the time. Figure 7.5, it will be straight line the parallel to y-axis figure 7.5. So the velocity time graph for a car moving with a uniform velocity of 40 km. However, we know that the product of the velocity and the time give displacement of an object moving with the uniform velocity. The area enclosed by the uniform time graph and the time axis will be equal to the magnitude of the displacement. To know the distance moved by a car between T2 T1 and T2 using figure 7.5 to draw the perpendicular from the point corresponding to the time T1 and T2 on the graph. The velocity of the 14 km per hour is represented by the height AC or BD, and the time T2 minus T1 is represented by the length AB. So the distance is moved by a car in time T2 minus T1 can be expressed as AD CD. S is equal to A into AC into CD. Here we see the formula. We can also study about a uniform acceleration motion by plotting its velocity time graph. Considered a car being driven along a straight line for testing its engine. Suppose a person sitting next to the driver records its velocity after 5 seconds by noting the reading of the speedometer of the car, the velocity of the car in kilometer per hour, as well as in the ms power minus 1 at different of time is shown in table 7.3, and we see that table 7.3 here. In this case, the velocity time graph for the motion of the car is shown in figure 7.6. That nature of the graph so that the velocity change by equal amount is in equal interval of time. Thus, for all uniform acceleration motion, the velocity time graph is a straight line. You can also determine the distance moved by the car from its velocity time graph. The area under the velocity time graph gives the distance magnitude of displacement moved by the car in the given interval of time. If the car would have been moving with a uniform velocity, the distance traveled by it would be represented by the area ABCD under the graph figure 7.6. Since the magnitude of the velocity of the car is changing due to acceleration, the distance traveled by the car will be given the area ABCDE under the velocity time graph figure 7.3. This is here we see the formulas of this. In the case of non-uniform accelerated motion, velocity time graph can have any shape. Here we see the graphs. Figure 7.7 shows the velocity time graph that represent the motion of an object where whose velocity is decreasing with the time, while figure 7.7 shows the velocity 7.7b so the velocity time graph representing non-uniform variation of the velocity of the object with time. Try to interpret these graphs. Here we see the table number 7.4 plot. Here we see the another table 7.5, and here we see the questions. 7.5 Equation of motion. When an object moves along with a straight line with a uniform acceleration, it is possible to relate its velocity, acceleration during motion, and distance covered by its certain time interval by a set of equation is known as the equation motion. For a convenience, a set of three such equation given below. Here we see the equations given below. Where u is the initial velocity of an object which moves with a uniform acceleration a for a time t, and v is the final velocity, and f is the distance traveled by object in time. In equation 7.5 describes the velocity time relation, with the equation 7.6 represent the position of the time relation. Equation 7.7 which represent the relation between the position and the velocity can be obtained from the equation 7.5 and 7.6 emulating t. These three equations can be derived from the graphical method. Here we see the numerical of the question, and the another exam the other another numerical, and here we see the another numerical of this. 7.6 Uniform circular motion. When a velocity of an object changes, we can say that the object is accelerated. The change in the velocity could be due to change in its magnitude or the direction of the motion, or both. Can you think an example when an object does not change its magnitude, the velocity, but only its direction motion? Let us consider an example of the motion of a body along a closed path. 8.1 8.9 so the path of an athlete along along a rectangle track ABCD. Let us assume that the athlete run at a uniform speed on a straight parts AB and BC and CD and D of the track. In order to keep himself on a track, he quickly changes his speed in the corner. How many times will the athlete have to change his direction of motion while he complete one round? In it is clear that to move in a rectangle track, once he has to change his direction of the motion 4 times. Now suppose instead of the rectangle track, the athlete is running along a hexagonal shape path A B C D E F as shown in figure 7.8. The situation, the athlete will have changed direction 6 times while he is completing one round. When if a track are not hexagonal but a regular octagon with 8 equal sides are shown by A B C D E F G H in figure 7.8 C. It is observed that as the number of the side of the track increasing, the athlete had to take a turn more and more often. We would happen to the shape of the track as we go on increasing the number of the side indefinitely. If you do this, you will notice the shape of the tract approaches the shape of the circle, and and the length of each side will decrease at a point. If the athlete moves with the velocity constant magnitude along the circular path, the only change in his velocity is due to the change in the direct motion of the motion of the athlete moving along a circular path is therefore as an example of an accelerated motion. We know that the circumference of the circle radius r is given by 2 pi r. If an athlete take t second to go on the round circular path of the radius r, the speed v is given by v is equal to 2 pi r upon t. When an object moves in a circular path with a uniform speed, it is called the uniform circular motion. Here we see the activity 7.11, and now we just finished our chapter. Here we learned, here we summarize the chapter. Motion is a change of position. It can be described in terms of the distance traveled by distance moved or a displacement. Second point, the motion of an object could be uniform or non-uniform depending on whether its velocity is constant or changing. The speed of an object is the distance covered per unit time, and the velocity is the displacement per unit time. Another point is the acceleration of an object is the change in velocity per unit time. Next, the uniform and non-uniform motion of object can be shown through graphs. The motion of an object moving a uniform acceleration can be described with the help of the following, namely, here we see the different kind of equations where u is the initial velocity of object which moves with the uniform acceleration a for a time t. V is its final velocity, and s is the different distance it travel in time t. Time t. If an object moves in a circular path with a uniform speed, its motion is called the uniform circular motion. Here we complete the above chapter, and here we see the exercise of this. So thanks for watching.